whole slide. It was such a great moment. This is the Synapse 1. This is incredible, you guys. Synapse 1. This is Synapse 1, 1992. It runs neural networks 8,000 times faster than CPUs at that time. Isn't it incredible? So this is the world's AI computer. And Roland just wants to, never forget that, Jensen. Never ever forget that. I said, okay, all right. I'll tell it, and I'll even tell everybody. Siemens 1992. Siemens 1992. We have a great partnership with Siemens and Roland Busch, the CEO, is supercharging the company so that they could completely leap the last IT industrial revolution and fuse the industrial capabilities of Europe, the industrial capabilities of mind of Siemens, with artificial intelligence and create what is called the industrial AI revolution. We're partnering with Siemens on so many different fronts. Everything from design to simulation to digital twins of factories to operations of the AIs in the factories, everything from end to end. And it just reminds me how incredible the industrial capabilities of Europe is, and what an extraordinary opportunity this is for you. What an extraordinary opportunity, because AI is unlike software. AI is really, really smart software. And this smart software can finally do something that can revolutionize the very industries that you serve. And so we made a love letter video, if you will. Let's play it. It began here. The first industrial revolution. Watt's steam engine and the mechanized loom introduced automation and the advent of factories, and industry was born. The age of electricity. Ampere unraveled electromagnetism. Faraday built the first electric generator, and Maxwell laid the foundations for modern electrical engineering. Siemens and Wheatstone's dynamo, the engine of electricity, bringing machines, trains, factories, and cities to life, electrifying the planet, igniting modern manufacturing. And today, born out of the computing and information age, the fourth industrial revolution, the age of AI, reimagined every part of industry. Across the continent, industrial AI is taking hold. From design to engineering, you're blazing new trails toward understanding and reinvention. You brought the physical world into the virtual to plan and optimize the world's modern factories. You're building the next frontier, where everything that moves is robotic. Every car, an intelligent autonomous agent, and a new collaborative workforce to help close the global labor shortage gap. Developers across the continent are building every type of robot, teaching them new skills in digital twin worlds and robot gyms, preparing them to work alongside us in our factories, warehouses, the operating room, and at home. The fourth industrial revolution is here, right where the first began. What do you think? I love that video. You made it. That's so great. You made it. Well, working on industrial AI with one company after another. This is BMW building their next generation factory in Omniverse. This is, I don't know how to say it. Can somebody teach me? Mujes? Sounds good. Exactly. That's exactly right. Good job. Good job. That's exactly right. They're building, of course, their plants, digital twins in Omniverse. This is Kion, their digital twin for warehouse logistics. This is Mercedes-Benz and their digital twins of their factories built in Omniverse. This is Schaeffler and their digital twin of their warehouse built in Omniverse. This is your train station here in France, building a digital twin of their train stations in Omniverse. And this is Toyota building a digital twin of their warehouse in Omniverse. And when you build these warehouses and these factories in Omniverse, then you could design it, you can plan it, you can change it. In greenfield is wonderful, in brownfield is wonderful. You can simulate its effectiveness before you go and physically lift and move things around to discover it wasn't optimal. And so the ability to do everything digitally in a digital twin is incredible. But the question is, why does the digital twin has to look photoreal? And why does it have to obey the laws of physics? The reason for that is because we wanted ultimately to be a digital twin where a robot can learn how to operate as a robot. And robots rely on photons for their perception system. And those photons are generated through Omniverse. And robots needs to interact with the physical world so that it could know whether it's doing the right things and learn how to do it properly. And so these digital twins have to look real and behave realistically. Okay, so that's the reason why Omniverse was built. This is fantastic. This is a fusion reactor digital twin. Incredibly complicated piece of instrument, as you know, and without AI, the next generation fusion reactor would not be possible. Well, we're announcing today that we are going to build the world's first industrial AI cloud here in Europe. I'm going to announce, These industrial AI clouds are, yes, a whole lot of computers in a cloud. However, its requirement, its performance, its safety requirements fundamentally different. And so I'm going to tell you a lot more about it on Friday. I'm only teasing you part of the story today, but this industrial cloud will be used for design and simulation, virtual wind tunnels that you just walk into. Virtual wind tunnels you just move a car into and you see it behave. Open doors, open windows, change the design. All completely in real time. Design in real time, simulate in a digital wind tunnel, digital twin of a wind tunnel in real time, build it in a factory, of a digital factory, digital twin in real time. All of this, and the robots learn how to be great robots and build the robots of our future, self-driving cars and such. We already have tremendous ecosystem here. We've been here, as you know, for a very long time. NVIDIA is 33 years old. The first time we came to Europe was during the time when workstations and the digitalization of products, CAD, the CAD revolution started. We were here doing the CAE revolution, and now the digital twin revolution. Some $2 trillion of ecosystem here in Europe that we partner with and that we have the privilege of supporting. What comes out of that is a new revolution that's happening. As you know, everything that moves will be robotics. Everything that moves will be AI driven. And the car is the most obvious next one. NVIDIA builds the AI supercomputers to train the model. The AI supercomputer for Omniverse digital twins. We also build the AI supercomputers for the robots itself. In every single case, whether it's in the cloud, for Omniverse, or in the car, we offer the entire stack. The computer itself, the operating system that runs on top of this computer, which is different in every single case. This computer, high speed, sensor rich, must be functional safe. In no circumstance could it fail completely. And so the safety requirements are incredibly high. And now we have an incredible model that sits on top of it. This model that sits on top of it is a transformer model. It's a reasoning model. And it takes sensor in, you tell it what you want it to do, and it will drive you there. It takes pixels in, and it generates path plans output. So it's a generative AI model based on transformers. Incredible technology. NVIDIA's AI team, AV team, is incredible. This is the only team that I know that has won end-to-end self-driving car challenge at CVPR 2 years in a row. So they're the winner again this year. Let's take a look at the video. Yep, thank you. Like any driver, autonomous vehicles operate in a world full of unpredictable and potentially safety-critical scenarios. NVIDIA Drive, built on the Halo safety system, lets developers build safe autonomous vehicles with diverse software stacks and sensors and redundant computers. It starts with training. Safe AVs need massive amounts of diverse data to be able to address edge cases. But real-world data is limited. Developers use NVIDIA Omniverse and Cosmos to reconstruct the real world and generate realistic synthetic training data to bring diversity to the AV model. The model can perceive and reason about its environment, predict future outcomes, and generate a motion plan. And for decision-making diversity, an independent classical stack runs in parallel. Guardrails monitor safe performance, and in cases of anomalies, calls the arbitrator to make an emergency stop. Further diversity and redundancy are built into the sensor and compute architecture. Each sensor connects to redundant computers, so even if a sensor or computer fails, the vehicle stays safe and operational. And in the event of a critical failure, the system can execute a minimum risk maneuver, like pulling over to the shoulder. Safety is foundational to autonomous driving. NVIDIA Drive lets developers worldwide integrate Halos into their own products to build the next generation of safe AVs. A billion cars on the road, 10,000 miles a year on average, 10 trillion miles. The future of autonomous driving is obviously gigantic, and it's going to be powered by AI. This is the next gigantic opportunity, and we're working with enormous companies and really fantastic companies around the world to make this possible. At the core of everything we do here with AV is safety, and we're really, really proud of our Halo system. It starts with the architecture of the chip, and then the chip design, and the systems design, the operating system, the AI models, the methodology of developing the software, the way we test it, everything from the way we train the models, the data we provide for the models, all the way to the way we evaluate the models. NVIDIA's Halo system and our AV safety team and capabilities are absolutely world-renowned. This computer was the first one to be software-defined. The world's first software-defined, completely 100% software-defined AI-driven software, AI-driven stack for AVs. We've been at this now for coming up on 10 years. And so this capability is world-renowned, and I'm really proud of it. The same thing that's happening for cars is happening for a new industry. As I mentioned earlier, if you can generate video from prompts, if AI can perceive, it can reason, and it can generate videos and words and images, and just now with cars, the path, the steering wheel path, why can't it also generate locomotion abilities and articulation abilities? So that fundamental ability for AI to revolutionize one of the hardest robotics problems is around the corner. Humanoid robots are going to be a thing. We now know how to build these things, train these things, and operate these things. humanoid robotics is going to potentially be one of the largest industries ever. And it requires companies who know how to manufacture things of extraordinary capabilities. This speaks of the European countries. So much of the world's industries are based here. I think this is going to be a giant opportunity. Well, let's say it's 1 billion robots around the world. The idea that there will be 1 billion robots is a very sensible thing. Now, why hasn't it happened? Well, the reason for that is simple. Today's robots are too hard to program. Only the largest companies can afford to install a robot, get it to teach it, program it to do exactly the right things, keep it sufficiently surrounded so that it's safe. That's the reason why the world's largest car companies all have robots. They're large enough, the work is sufficiently repetitive, the industry is at a sufficient scale that you can deploy robots into those factories. Almost everybody who's a Mittelstand or small, medium companies or mom and pop restaurants or stores or warehouses, it's impossible to have that programming capability until now. We're going to give you essentially robots where you could teach them. They'll learn from you. Just as we were talking about agentic AI, we now have humanoid AI that can learn from your teaching using toolkits that are very consistent with the NEMO toolkits I spoke about. NVIDIA here as well is built in 3-layer stack. We built the computer, the Thor computer dev kit looks a little bit like this. This is a robotic computer, completely self-contained dev kit, sits on your desk. These are all the sensors, and inside is a little supercomputer Thor chip. It's really, really incredible. And these, yep. I could imagine getting one of these inserted. Okay. Thank you, Jimmy. And so that's the Thor processor. On top is an operating system designed for robotics, and on top of that, transformer models that take sensor and instructions and transforms it and generates flight or paths and motor controls for arm articulation, finger articulation, and of course your legs articulation. Now, the big challenge of humanoid robotics is the amount of data necessary to train it is very, very hard to get. And so the question is, how do you do that? Well, the way you solve that problem is to back in Omniverse, a digital twin world that obeys the laws of physics. And this is an incredible piece of work that we're doing. Don't do it. Don't. Oh, my fault. Okay, these are robots. We developed computers to simulate, to train them, computers to simulate them, and the computer that goes inside them. There's a whole bunch of human robotics companies being built around the world. They all see the great opportunity to revolutionize this new device, if you will. And the progress is going incredibly fast. And the way that they all learn is they learn in a virtual world. And this virtual world has to obey the laws of physics. And recently, we announced a big partnership with Disney Research and DeepMind. And we're going to work together to create the world's most sophisticated physics simulation. And I'm just trying to figure out, at this point, how to go to that slide. Teach me. Who's with me?